Okay, thank you. And let me also thank the organizers for making this conference happen and inviting me to give this talk here. Yes, so I'm going to speak about the research that we did with Gianni Manno. When I prepared the talk, I noticed it would be good to start with a two-dimensional case before I speak about the three-dimensional case that we that should be the main part of my talk. So yes, the first half will be about the two-dimensional case, about the classical Lie problem of finding or describing the metrics, the surfaces with projective symmetries. I will also briefly mention the link to integrable systems. And then in the second part, which is the main part, I will speak about dimension 3 and our solutions for Levi Civita metrics, which in particular cover the Riemannian metrics with projective symmetries. And our approach to this topic was a bit different from the one used in dimension 2, because we were using an approach invented by Alexander Solodovnikov in the 1950s, which for the three-dimensional case turned out to be very useful. And yes, I will also show you some of the normal forms we found. So this is based on this paper on the archive, which was recently accepted and will be published soon. So it's actually already available online in Journal de Mathématiques. So first of all, I should introduce a little bit, because my talk is going to be very different from the previous talks that we heard today. So I should introduce the geometric background a little bit. So we start with the manifold with the Riemannian metric. And we all know, of course, the geodesic equation. I will speak today not about geodesics in particular, but about reparameterized geodesics. So I look at what is called pre-geodesics or unparameterized geodesics. And as I said, in the first part, I will speak about dimension 2. And in dimension 2, you can change your parameterization of the geodesic equation and using one of the coordinates, which gives you this what is called a projective connection. So in dimension 2, you just have one ODE of this form. In higher dimensions, you get more of these equations. And as you see here, the coefficients depend, if you start from a metric, on the Christoffel symbols, but there is some freedom in here. Okay, so we are looking at metrics with projective symmetries. And the simplest example are Killing vector fields, so local isometries. But there are more than just local isometries. So a projective vector field is a vector field such that its local flow preserves geodesics, but geodesics in this wider sense that you can change the parameterization. So they should preserve the curves, but not necessarily the parameterization of the geodesics. Killing vector fields also preserve the parameterization, if you like. So those are the simplest example. But then you can also have homotheties, so stretchings, which are slightly more general. But then everything else I will just put together under the name essential projective vector fields. And those are the projective symmetries that I'm interested most today in. Right. So this is the setup. Let's speak quickly about the constant curvature case. So constant curvature metrics will be, I will mention them every now and then, but they are not what I will focus on. So Beltrami showed in the 1860s that if a manifold has constant curvature, then its projective algebra is 8-dimensional. And of course, you have the Killing vector fields. You have a proper homothety, and you have essential vector fields. So for essential vector fields, which are shown here, the last picture actually should be printed twice, but there wasn't space. But you see the two symmetries are almost the same up to changing the roles of X and Y. So those essential projective vector fields are the vector fields that I'm interested most in today. And on my first slide, I already had the name Lie problem. So Lie was considering metrics with projective symmetries. And for dimension 2, he showed that if you have a non-trivial projective symmetry algebra, so trivial here means just 0, which is, of course, not really an example, then you basically just have 2 or 3 cases. So you could have a one-dimensional symmetry algebra. You could have a 2-dimensional symmetry algebra or a 3-dimensional symmetry algebra. But then he shows that if you don't have any of these 3 cases, you are in a constant curvature case. So those are the 4 cases that you need to consider. And of course, Beltrami already solved the constant curvature case, so only 3 cases left. And this is the Lie problem in dimension 2 originally. So first I attempted, the original is in German, but first I attempted a literal translation, which maybe seen from today is a bit clumsy. So he says the task is to determine the form of the arc element of each surface whose geodesic curves admit an infinitesimal transformation. And by infinitesimal transformation, he means exactly projective vector fields. So maybe a more modern version of this problem would be to say the task is to describe all 2-dimensional metrics that admit projective vector fields. And the 2-dimensional case is considered to be solved. There are still some issues left with singular points where your symmetry is degenerate. But if you leave out this problem and you just care about generic points on your manifold, then the 2-dimensional case is solved. And here is a list of references where the solution is obtained. So maybe it's a good idea to start with Aminova. However, her proof for the case of a symmetry algebra of dimension 2 or 3 had a gap, which was filled by Bryant, Mano, and Matveyev some years ago. And the last 2 references are for the case of a one-dimensional symmetry algebra. So now I just want to give you a quick overview over the 2-dimensional case. As I said before, the 3-dimensional case is what I really want to speak about, but I felt it's a good idea to start with the 2-dimensional case, especially because we use the solutions from the 2-dimensional case to find the normal forms in the 3-dimensional case. Okay, so I already mentioned it, but here is it again in a graphical version. So in dimension 2, you should consider the following 4 cases. The case of a maximal, of the maximal case, the maximum dimension of the symmetry algebra is 8, but this is already constant curvature. So this is what Beltrami already solved for us. And then you're left with these 3 cases. The first case here, symmetry algebra of dimension 1, I will come to in a moment. At the moment, I will focus on those 2 cases. And you see here, I labeled them as integrable case and superintegrable case. I will also show you what I mean by this. Okay, so here is the first theorem proven by Bryant, Mano, and Matveyev. And this considers the case when you have a metric of non-constant curvature where the projective symmetry algebra has dimension 2 or 3. So exactly those 2 cases in the middle in that tree here. So, and they show that, okay, I actually included a constant curvature case here. So if you have a symmetry algebra of dimension at least 2, then you either have constant curvature, but then you have the 8-dimensional symmetry algebra, or you have so-called Darboux-Königs metric, which would be the superintegrable case, the symmetry algebra of dimension 3, or you have one of those 3 cases. And these 3 remaining cases are the case of a symmetry algebra of dimension 2. And the proof in this work is to take the projective connection and to find a normal form for it. Actually, you have 2 different cases here where the parameters have to satisfy some values. So for example, here, if you have equality, then you would end up in the superintegrable case. And then you study the solutions for those differential equations. So this is, let's say, the classical approach to it. And then you end up with the normal forms. However, the problem is that this did not work for a one-dimensional symmetry algebra. And so Vladimir Matveyev found a way to circumvent this issue. And the idea was to not use the projective connection, but to use the metrization equation. So if you have a projective structure, that means a projective equivalence class of connections, connections which admit or which have the same geodesics up to reparametrization. And then you're looking for metrics that realize this projective structure through their Levi Civita connection. And the question or the answer to this question, so what are the metrics that realize a given projective connection through their Levi Civita connection, is answered by this equation here. So to start with, this problem is a highly nonlinear problem. But if you change from looking at components of the metric to looking at components of a certain weighted tensor density, then the problem becomes a linear problem. So that is the main message. And this is the equation, but the important thing is it's a linear equation. And this, the space of these sigmas of those solutions to this linear equation is, of course, invariant under the action of the projective symmetry algebra. And this was what Vladimir started from to attack this case of a one-dimensional symmetry algebra. Okay, so now you should distinguish. So we fix our dimension of the symmetry algebra. So we want a one-dimensional projective symmetry algebra. But now we can distinguish according to the size of this space of solutions to this linear equation that I just showed you. And there you have 3 cases. In the first case, you just have a one-dimensional space of solutions, which means that all metrics that realize this projective structure are just proportional to each other. And this is a case, in the beginning I mentioned, I'm only interested in these essential projective symmetries, the ones that are not just stretchings or killing vector fields. So this first case I'm not really interested in today. I'm interested in the cases where you get these more interesting, non-trivial, essential projective vector fields. And again, you have 2 cases, an integrable case and a superintegrable case. In the integrable case, you have a 2-dimensional space of solutions to this linear problem. And it's integrable because this fact will give you 2 integrals of motion, the Hamiltonian, so to say, and an additional one. So you get an integrable system. And in the superintegrable case, you actually have 3. So let's start with the superintegrable case. And here we can write down the following theorem, proved first by Vladimir Matveyev and then refined in a paper with Gianni. So if you have a 2-dimensional metric with a 1-dimensional projective symmetry algebra falling into this superintegrable case, then it will be one of these metrics, which are parametrized through theta and phi. And you see here, I said before, the space of solutions of this linear problem is three-dimensional, and that means you provide here three metrics, which stand for the three basis vectors of the space of solutions. But then some of these solutions, if you just write down the linear space of solutions, some are diffeomorphic, and if you remove this ambiguity, you end up with only those metrics written here. Okay. And now this was the superintegrable case, but now let's include this integrable case where you have a two-dimensional space of solutions to this linear problem. And then you end up with the following statement. So now we are in the case that we have a one-dimensional symmetry algebra, or actually I can include into the theorem also the ones with higher symmetry algebra, because you can show that they can all be written down as here in this displayed formula, because they all admit a homothety or a killing vector field. So the equation here in the middle, it includes all the constant curvature cases, all the cases with the symmetry algebra of dimension 2 or 3. And we are left with only the superintegrable case or the integrable case of the second part of the problem, where you have a one-dimensional symmetry algebra. And you end up with a list of normal forms that looks like this. And this is the worst slide that I have today, so I'm skipping it immediately. Because I guess at this time of day, we're not interested in all those details. And you can always look them up in the paper. So what I will do instead, I will just pick a selection of metrics, which is still enough to give you a taste of how it looks like. So I will just show you the Riemannian metrics, or actually there are non-Riemannian, pseudo-Riemannian ones among those, but they contain the Riemannian ones. And I will focus just on giving you the metrics without homothetic vector fields that just have an essential protective symmetry. Yeah, sure. Yes. What's that? Sorry. No, so those results are all local. Yes, I should have said this in the beginning. Yes.
So you're not talking about global?
No, no, just local. Yeah, sorry, I should have clarified this in the beginning. Yes, so this is all local. Yeah. Yes, they are quadratic in momenta because they basically come from metrics. So metrics are two tensors, so all the integrals that you get are quadratic in momenta. Okay, more questions? Yeah, actually, maybe this will clarify now the connection to integrable systems. So what you do, you take one of those metrics and you define a Hamiltonian from them by contracting with the momenta. And I said before, you have at least, in the cases that I'm interested in, you have at least two independent metrics that share the same geodesics up to reparametrization. And this allows you to not just write down the Hamiltonian, but also another integral, which I call f here, which is defined from another metric that has the same geodesics as the metric G. And this is something that goes back to Polivet from the 19th century. So if you have a pair of projectively equivalent metrics, so two metrics that share the same geodesics up to reparametrization, it allows you to write down Hamiltonian and a corresponding integral of motion. And this, of course, defines in dimension 2 an integrable system. So this is why it's enough to have a two-dimensional space of solutions to this linear problem that I showed you before to define an integrable system. And you need a higher dimension for the space to get out a superintegrable system. And I mean, this is for dimension 2. So this looks very specific. But again, Vladimir Matveyev and Peter Topalov showed that, that this is actually something that works in any dimension. So whenever you have a pair of projectively equivalent metrics, it defines an integrable system. And here is the procedure how you can do that. So you define first a 1-1 tensor using the two metrics that you have. I mean, this is the only information that you really can use. So it's natural to define this 1-1 tensor. And then you compute its characteristic polynomial. And the coefficients in this characteristic polynomial give you the coefficients down here, where you define several 1-1 tensors that finally give you the integrals that make up your integrable system. So the message here is, if you have a pair of projectively equivalent metrics, so two metrics that share the same geodesics up to reparametrization, this defines an integrable system. Yes, yes, the powers of G. And if you look at this equation, if you set small k equal to 0, it will give you back basically an integral of this type. And if you put in n, so you can go up to n-1. And if you go further, then you just get nothing new. You just get linear combinations of the other ones. If you put in this maximal value, then you end up with the multiple of the Hamiltonian. Yeah.
So this is a integral system in what space?
So the space is the manifold with the metric. Exactly. Yes. 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 So yes. So maybe I should have put this here. So you have this Hamiltonian, which is a function on the cotangent space of the manifold that I started with. Okay. More questions? So again, so this gives you an integrable system whenever you have a pair of projectively equivalent metrics. And here is the superintegrable case. So now you need more than just a pair of metrics. But in the example that we had before, we actually had 3 independent metrics. So we have a good chance to get a superintegrable system out of this. So let me skip back just to show you again which system I'm talking about. It's this one. So here you have 3 metrics that are not linearly dependent. And this, as I said, gives you a superintegrable system. And those are the systems that we that I have on this slide. So by a superintegrable system, I mean a superintegrable system in the sense that I have 2n-1 functions on the cotangent space that commute with the Hamiltonian, but I don't require to have a subset of n commuting integrals of motion. So it's a bit weaker maybe than complete integrability, but of course you have more integrals of motion. I require them to be functionally independent. And the first one, just by convention, should be the Hamiltonian. So now if you go back to this tree that I had in a previous slide, you have 3 candidates basically for superintegrable systems. Of course, you have the constant curvature case. And we know that there are many superintegrable systems, and they are classified by Kalnins, Miller, Kress, and so on. Then you have those Darboux-Königs metrics, which are also known to be superintegrable. And they admit a 2-parameter potential. So now I'm taking the Hamiltonian, but I'm allowing to add a potential which depends on position. Yeah.
Do you require the first and F to
be? No, exactly. So I do not require that and many of those to commute. I don't require this. Yes. Thanks for the question. Yes. Yes. I mean, if you just pick two of those metrics, it defines your integrable system. No, not this definition. No. In this definition, no, I don't require it. Exactly. Yes. Yeah. So in my definition, I do not require a subset of commuting integrals of motion, but by construction, I can just pick two of those three, let's say, metrics, and this defines an integrable system in the usual Liouville-Arnold sense. It seems to me that there are two different conflicting definitions. So in this classification community for superintegrable systems of second order type, so this is actually the definition that is used for this classification. So yeah, to me it seems that there are two conflicting. Mm-hmm. Yeah.
I understand that motion is curved now, but
one-dimensional rhetoric. You have terminus one integral, so they have one dimensional scope.
yeah, but if there is an actual variable C, for example, so that it's from time to time. But they do the same stuff.
One-dimensional fiber, one-dimensional toroid. What do you want to say?
But yeah, how can you find it?
Yes, let's maybe talk about this afterwards. How am I on time? Okay, roughly 20 minutes. Right, so those are the two cases that are classically known, let's say. But now the system with the three independent metrics that I showed you before actually gives us new examples of, or actually they kind of are included in this classification, of course, but additional examples of metrics that are superintegrable. And you can actually show that they admit a 4-parameter potential. So they are what is called a non-degenerate superintegrable system, or plural systems, because you have this entire space of projectively equivalent superintegrable systems with the 4-parameter potential. Okay, so this is the two-dimensional situation, and now I will start to speak about what I really want to speak about, the three-dimensional case. And in the three-dimensional case, that's the first thing, maybe bad news. So we had several superintegrable systems in the two-dimensional case, but in dimension 3, you can't really hope to get those, because there is this theorem by Vladimir Matveyev and Kiosak, who showed that for three-dimensional metrics, and the reason is a curvature argument because the Weyl tensor vanishes for three-dimensional metrics. If you don't have constant curvature, then at most your degree of mobility, so this dimension of this linear linear space of solutions to this linear equation that I showed you, is at most 2. And I mean, 2 means you get one pair of equivalent metrics. So that's enough for integrability, but not for a superintegrable system. So the bad news is in dimension 3, we can't really hope to get interesting superintegrable systems, but still we get interesting integrable systems. Yes, I mean, I should also mention that the superintegrable systems in dimension 3 on constant curvature spaces are classified. Okay, but now let's really speak about the metrics that are projectively equivalent in dimension 3. And I will focus on Riemannian metrics, but actually what we showed is a little bit more general because we look at Levi Civita metrics. And all the interesting Riemannian examples are among these Levi Civita metrics. So the metrics look like this in the Riemannian case. And or actually, this is one type which was considered by Alexander Solodovnikov in the 1950s. And there is another type which is probably more interesting than this one. But let me start with Levi Civita's classification of pairs of metrics that have the same geodesics up to reparametrization. And the original is in Italian. And you see here, this is for any dimension, and the normal forms that he gets, they look, they are quite long. So down here in the green box, I show you only the cases for dimension 3, and then you end up with just 2 cases. And I just write down the metrics up here. Of course, the second equation, 33 in Levi Civita's work, gives you this, another metric. So as I said before, you can have at most 2 projectively equivalent metrics in dimension 3 if you don't have constant curvature. So this is one of them, and the other one you get from this formula. And this gives you the integrable system, the combination of G and this companion metric up here. And you have 2 cases, which I label 1, 1, 1, because in the 1, 1, 1 case, you have 3 functions in one variable that define your metric. And in the 2, 1 case, you have a 2-dimensional metric and 1 univariate function. Okay, and here is the tree of cases that you need to consider. Again, I will not consider the constant curvature case. In this case, in the case of constant curvature, you have 10 linearly independent, well, solutions to this linear equation, but let's say 10 independent metrics. In the constant curvature case, I will not consider the constant curvature case. And then you have this, what I call self-similar case, when you just have one metric and all the metrics with the same geodesics up to reparametrization are just multiples of this. And this doesn't give you an integrable system, so I'm not interested in it in this one. So I end up with just 2 cases, and that's the 1, 1, 1 case and the 2, 1 case from Levi Civita's classification. So now I consider those 2 metrics. And for the first one, as I said before, Alexander Solodovnikov was already writing down or was already considering trying to solve for all the projective vector fields and the metrics that admit those. And he ended up with these 2 systems of equations. So those are ordinary differential equations for the functions vi, which just depend on one variable each. So these are the components of the projective vector field, and the functions xi, which describe the metric. So you end up with 2n equations for 2n functions, v1 to vn, because your manifold has dimension n, and x1 to xn. Of course, you know the solutions exist, but to write them down in general is not very nice. But in dimension 3, you are lucky because the second set of equations here will not depend on xi. So this is very simple to solve. I should also say something about the difference between the yellow and the green box. So you could write them all down in a uniform way, but Solodovnikov chose to separate them up into these 2 kinds, because the yellow box is the projective symmetries that are essential. So here you don't get homothetic vector fields, but only essential ones. And over here in the green box, you just get the homothetic or killing vector field and not essential projective symmetries. The problem maybe, or the difficulty with this separation is you have to check in the end the metrics that you find here. So these solutions xi that you find here might correspond with solutions xi over here. They might be the same metric because the same metric can have killing vector fields and essential projective vector fields or homotheties and so on. Okay, but if you take care of all this and if you solve the ODEs, so again, I'm mainly interested in the equations in the yellow box. You end up with solutions for the metrics and for the projective vector fields. And again, I'm just showing you a selection. So we found the following 3 cases. If you just look at metrics that don't have homotheties, so not self-similar metrics, so just an essential projective vector field and only the Riemannian case, then you end up with these 3 cases. And just to remind you, there are many normal forms that I don't show you, so you can look them up in the paper if you like. Okay, so that was just the 1-1-1 case. So the simplest case where you have a metric that just depends on 3 univariate functions. And I mean, this case is sort of easy because Solodovnikov already gave us the ODEs. So we just had to solve them. The more interesting case is this case where you have a 2-dimensional metric that you can choose freely. So the metric again is the one up here. It depends on a 2-dimensional metric that you can just choose. So that could be anything and a univariate function. And now you should find the projective vector fields emitted by these metrics, and you should find the size, the zeta functions here. So the zeta of x, such that the metric actually admits such a projective symmetry. And here I already use a result by Alexei Boltynov and Vladimir Matveyev, who showed that the distributions belonging to those coordinates x and y1, y2 are integrable. And so you can assume that the projective symmetry has this form here, which of course simplifies the problem. You could also get, of course, this form by just stubbornly solving the equations, but it's easier to just start with that. Okay, so our task now is to find the metric. So basically these functions and the matrix H here, such that we can find non-trivial solutions V. And then we should also find the components V1, V2, V3. And this is the most important tool that we use to get to these solutions. And you see here, what we find is a system of ODEs again, very similar to the ones that Solodovnikov found. So I start with the metric and the projective vector field here. And we show the following. We show that this is not just a formal decomposition into a 1-dimensional and a 2-dimensional component, but actually the 2-dimensional component has to be a projective symmetry for this 2-dimensional metric here. And not just a projective symmetry, but actually it has to be a homothetic symmetry. So either a proper homothety or a killing vector field. So it's basically a very simple symmetry that you can just have on the 2-dimensional block here. And then you need to add one more dimension to it. And what can you add to it? Well, this is given by the system of equations down here. And as I said before, this is very similar to the equations Solodovnikov found. So the first component of your projective symmetry and the function zeta of x, which describes your metric, they have to satisfy this ODE system. Now it's not as simple as the system that we had before, because now the second equation depends on zeta, but still it's a simple system and you can solve it. And you end up with solutions. Again, I'm just showing you a selection, just some examples. What you find is that the metric should be one of these three. Of course, now there is a lot of freedom here because you can put any suitable metric, any suitable two-dimensional metric in here. Here I have this assumption that H should not admit a homorphic, respectively a Keeling vector field. And this is because, again, here I restrict to metrics that don't have homothetic vector fields, but just essential projective vector fields. And here you have the symmetries. If I now would relax this assumption and would allow metrics with homothetic vector fields, then we can actually use this decomposition theorem from the previous slide and put in here the two-dimensional metrics from the first part of my talk to construct metrics with a higher dimensional symmetry algebra. So we can use the two-dimensional solutions and construct new solutions in high dimension from them. Again, I'm not showing you all the solutions that we found, all the normal forms that we found, but we'll just give you a picture again. So that's all. Thank you. Yeah.
Let's consider that one is a set of metrics that meet the essential projective vector.
Mm-hmm.
The other one is metrics that meet the projective vector. Are those sets right?
Well, I mean, so I showed you some examples where you have this degree of mobility equal to 1. So in this case, you can have projective symmetry, not an essential one, but all your metrics will be just multiples.
Yeah.
So in a sense, they are the same.
Well, if you have an essential projective vector field, you can blow the metric.
Yeah.
And you get a
Yeah.
projective vector.
Exactly, yes. So this will give you, let's say, non-trivial projectively equivalent metrics because they will not be just multiples of the